Good evening and welcome to our third Astrochat session, and wherein we are trying to make palatable, like the Golgappas and Bhelpuris, palatable, cutting edge astronomy, which has been presented in the 39th meeting of the Astronomical Society of India. One thing is that, of course, we may be very partially covering all of that, but whatever, whichever possible, we are trying to bring out the excitements. And helping us are the speakers themselves. And so we have with us Sarita Vich. Welcome, Sarita, from IIST, Tirunanthapuram. And Sarita, you are going to uh, before I go there, I just we have also several guests in our studio. They'll be coming in, several other speakers too, and we are going to give you a mix of various topics. I just wanted to tell our studio guests, when you would like to come in with some interjection and so on, please keep your video on. Then I will know that you want to interject. I can call you in. So, Sarita, you are going to tell the participants about some very exciting things you have found in terms of stars forming and the kind
Yes,
of gigantic clouds inside which they are formed, and once they are formed, how they are actually affecting the cloud themselves, some kind of feedback
yes,
from
yes.
them, and so on. So please take us through this.
So we
If
know,
you wish to share visuals, please add them using share,
okay,
and I will add them here.
fine. So I'll just start off, and in the middle, somewhere along the way, I'll share my screen. So we all see stars in the night sky, but do we really know how they are formed? So they are formed actually in clouds of gas and dust. We don't see them usually with our naked eye at night, but towards some regions you can see them. And these clouds of gas and dust is known as the interstellar medium, and the densest phase where the gas and dust is very dense, that is known as, those regions are known as the molecular clouds. And it is in this dense phase of the molecular clouds that stars usually form. Now, I'll just share my screen to show you one star forming region, because that will help me explain what I'm talking about. Okay, entire screen. Okay,
Yeah, I
so
have I
yeah,
do not yet see it in the studio.
yeah. Can you,
uh,
1 second? Can you see it now?
yeah, yes,
So,
it's there now. When you actually go full screen, you may not be able to see the studio, but if
no,
there's
but
any
that's all
need,
right.
you will be able to hear us.
Yeah. So this is one such region, a star forming region, which is seen with one of the telescopes, and you can see that this is a cluster of very young blue massive stars, and around this you see this lot of gas and dust. So the idea is to try to understand, what we work on is to try to understand how the process of forming stars itself dissipates or affects this molecular cloud. Okay, it can affect the star formation can affect the molecular clouds in multiple ways. You can see that there are many structures here, and we try to understand how this affects the cloud, and why these kind of structures are formed. And in some cases, for example, it can destroy the cloud entirely, whereas in other cases it can compress the cloud in the vicinity, for example, and lead to the formation of more stars. So this is what we try to understand, the feedback effect of the formation of stars on the molecular cloud in which it is forming. So this is another picture showing the same thing. Sorry. This is another picture showing the same thing. Here you can see that there is a cluster of stars, and these cluster is a group of stars formed at the same time from the same molecular cloud. So then you have this group of stars. In fact, the more massive stars. That means when I say a massive stars, its mass must be more than 10 times the mass of the sun. So these massive stars also give out during the various stages of evolution stellar winds. So winds are these particles which are given off along with radiation or light, electromagnetic radiation. It also gives off particles which are known as stellar winds. So this can interact with the surrounding medium, and it can give rise to this kind of disturbed or violent this violent phenomena disturbs the surrounding interstellar medium. As I said, in some cases, it can completely clear off the surrounding interstellar medium. In other cases, it can compress the gas to form more stars. And in this stellar feedback, this is just a schematic to show how it can lead to the formation of more stars. For example, if this is a group of stars, then because of the stellar winds as well as the radiation pressure, the molecular gas around it is compressed, and this compression, in this compressed region, you can also have another burst of star formation. So this is known as triggered star formation. This kind of feedback is known as positive feedback because the process of star formation triggers further star formation in the molecular cloud. You can also have negative feedback where, as I said, where it can completely destroy the molecular cloud. Then this is another region where people, for example, this is the region that the authors were trying to study a set of people. And as you can see, we are trying to understand how these kind of structures formed. And for example, to understand this, this is the schematic that they have come up with, that there is a really, there was a star here which underwent a supernova explosion because the massive stars can really evolve very fast as compared to low mass stars. So while the other stars are forming, the massive star can also lead to a supernova explosion. So as this explosion occurred, it caused a shock wave to pass through this cloud. And as it passed through the, as the shock wave passed through the cloud, in its wake, it left behind the highly disturbed medium, which actually there was a lot of gas motion and gas compressed and led to the formation of more stars. So this is the kind of feedback phenomena which are generally invoked, for example, to understand the star formation. Now, why is this important? Okay, see, this is important because we are still trying to understand. People are trying to see that there are molecular clouds, and they we calculate how much percent of gas in the galaxies or in molecular clouds in our galaxies is converted to stars. And it is found that there is a very small percentage of the gas which is converted to stars, and the rate at which this is forming stars based on simple calculation shows that it is a very slow process. So what is happening in between? So it and that in between thing is this feedback. It is slowing down the entire process of star formation. We know that if these feedback processes were not there, for example, in the Milky Way is our galaxy, there's a lot of gas and dust around and lot of stars. But if these feedback processes were not there, then the rate at which the stars would have formed would have been more than 2 orders of magnitude higher, and all the gas should have been converted to stars several billion years ago, and we should not have seen any gas around us. So we are in some sense trying to understand the evolutionary history of Milky Way, and what are the Milky Way and other galaxies, and what are the processes that go in to understand the star form, not only this process of star formation, but how it affects the further star formation. That is the evolution of the process of star formation itself. So yeah, Ratna, yes.
What is determining that there is feedback or there is no feedback? And
First is, we know that the stars, massive stars, give a lot of radiation. So this radiation affects the surrounding. So you can actually, as I showed you, we see the star forming regions which shows this highly tempestuous interstellar medium. We try to understand what can give rise to this, and to understand that, we look at the various aspects of a star formation that could give rise to this disturbance in the interstellar medium.
the picture is likely to be somewhat heterogeneous, like
Yes.
there may be supernova induced star formation kind
Ex-
of regions, and or
Exactly.
some other kind of differences as well.
Yes, and this is very interesting because here, as you know, in when we are talking about astronomy, we have just the snapshots of the sky. So we just see the star forming region, and then we have to try to understand why this happened here. So one way to understand the effect of various feedback processes is through simulations. And through simulations, for example, people put in a massive star and a molecular cloud, and then try to see the effect of radiation from this massive star on the cloud, the effect of stellar winds. And surprisingly, we are able we are able to replicate most of the structures seen from many of these processes that I talked about.
Litan, could I call you in at this point? And if you would also um, like to add any queries, etc. Also, from I mean, I'd like to ask you to step in now. Sarita, you were talking about feedback from the stars into the star cloud and so on. And Litan, you are going to tell us a little bit about the initial process itself, from
Of the star
the
formation.
cloud, star formation itself, and also the uh, formation of the planets and so on, and the very very exciting aspects related to the exoplanets. There's such a zoo of them. So, Litan, could you hear us? Would you like to put on your audio video at this stage? Is there any network issue? Uh, oh, I think we have lost him because of network issue.
Hear
Yeah,
me?
Arvind, I think Arvind has a question. So please go ahead, Arvind. Keep
Sarita,
your.
yeah,
Hmm.
can you hear me now?
Yes, yes.
Yes, yes.
Okay. Yeah, so the point is that I wanted to say that this molecular clouds and all this, I mean, the
Hello.
particle density is very low, isn't it?
Hi.
I mean, it is much.
I missed the point due to network issue.
Yeah, 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 yeah. So
Yeah.
after Arvind's question, then we
Yeah.
will just
Yeah.
go ahead,
That I just
Arvind.
wanted to point out to the young ones that the particle density is so low that it is better than vacuum that we produce here on
That's
the
right.
surface of Earth. And we see
That's
them
right.
as a cloud only because they are so far away. So together we see them as a cloud. But if we go close by, probably it will be just vacuum, or you will not see anything there. Isn't that true?
It, that's right. In fact, the interstellar medium has comes broadly classified into different phases, and the densest of them has a density which is lower than the best vacuum that you can achieve on Earth.
Oh,
So,
that's
yes, this is the densest one. This is where the stars form, and that is still lower than
well,
what you
lower
can
than,
achieve
yeah.
from.
Right.
And then it takes enormous amount of time for the cloud to contract before even you think of starting the star formation. Isn't that right?
Yes, yes. So the time scales here, when we talk about, is of the order of
Million.
several million years. That's
Million
right.
years. Yeah, yeah.
Yes, yes, and they evolve also on those time scales. That's why the importance of simulations, because ultimately what we see are snapshots. So we look at different snapshots and try to create a cohesive picture based on the statistics. That means you probably see different star forming regions in different evolutionary stages, and I think this is where Litan comes in. He can tell us how the initial stages, as the star formation progresses, how they study using various chemical traces, right?
Yep.
So over to you,
Yes.
Litan. And if you would like to share screen, there is a share button right in the center.
Yeah.
You could use that. And let
I'll
me
take
just.
my leave then. Bye.
Thanks so
Yeah.
much,
Thank you,
Sarita,
Saita.
Bye. Bye.
uh,
Bye.
for
Bye.
Bye.
walking us through that.
I don't know why it's not able
Uh,
to
there is a
share.
share button at the bottom
My
center.
browser blocked. Okay. Let me just. Okay.
Else you could mail it to me and I'll share it from here. That will take a little
Ah.
time, but meanwhile you could get started
Okay.
uh,
Okay. So, just give me a
telling.
moment because
Oh,
it
sure, sure,
seems
sure,
my
sure,
my
sure.
browser blocked me to.
Meanwhile, to tell the participants, we are kind of bringing these small, small nuggets from
Mhm.
the presentations which have been there. So we are going to have a mix and match kind of a session as we had for the last 2 days. So ahead of us, we are going to go way back uh, to the beginnings, but
Yeah.
not the very beginnings, but somewhat a little later phase, something called a reionization phase. We are going to come to that in a while. After that, we have some. Let me just see what do we have, what we have in store for you uh, while we are getting this. Or
Okay. So
I thought that you wanted me to fill in for a while later, and that's why I was
yeah,
talking.
yeah, yeah, yeah. Of
But if
course.
you'd like
So
to go ahead without the visuals for now, please
no,
do
no, no.
that.
So what I okay. So can you tell me your email so that I can share?
Oh, so
because
yeah, yeah,
probably
yeah, yeah. So send it to Nehru Planetarium at Gmail. That would be
okay,
simplest rather
okay,
than my name spelling.
oh, okay,
Nehru
okay,
Planetarium at Gmail, and I will then download it and put it here. And yes, so we are also going to bring to you something about cosmic rays from circumgalactic medium. We are going to talk a little bit about sun and of course the very exciting Aditya mission. Few nuggets here and there, and very interestingly, machine learning and astronomy towards the end of the session today. So stay with us. Oh, we lost Litton, I think. So, Arvind, I'm going to ask you to come in, and while I'm just trying to check that we are getting the
Yeah,
visuals.
I'm here.
So, all right. So, I there are a couple of other topics also, I think, which we are going to be covering, and yes, yeah. So, we have had discussions about a variety of contexts in which there have been exciting work which was done over the last year or so. So, one aspect which I have been mentioning several times when we were looking at many of these presentations, the kind of like the most of these endeavors that we have, what are they are kind of detective stories. Maybe something
Yeah.
is observed, and maybe we have some kind of model or something is existing, and perhaps then when something is observed, a signature is found which doesn't seem to be fitting that, and so on, then trying to find out what that signature means, and so on. So these are the science detective stories, and in these, when one is trying to maybe explain a phenomena, maybe there is some kind of acceleration of charged particles we are seeing, or there is some kind of enhancement of radiation one is seeing. So then the contexts which are invoked in this,
Okay,
um
Rachna,
they,
sorry.
yeah,
Shall
Arvind,
I
you
say
wanted to
something?
say something? Yeah, please
Yeah,
go ahead.
just as a filler, that about some about 50 years ago or around that time, Fred Hoyle wrote a technical paper in which he talked about these molecular clouds having the ingredients necessary for life on Earth, and some paper of that kind, which he submitted, and it was rejected because it's a new idea. People were not willing to accept. And then later on, he wrote a novel called Black Cloud. Fred Hoyle, he wrote this novel
Hmm.
in which
Yeah.
he said that the cloud itself was alive, and he said that
Huh.
why should we have life just the way we see it here, but the cloud itself can be alive. And after that, people started talking about a lot about life elsewhere in the universe. So
Hmm. Hmm.
uh, it was a
Yes,
beautiful novel.
yes,
It is
yes.
available as PDF file, and people should read it.
Hmm.
It is amazing piece of work by him.
Yes,
Can you talk about
and
this? Yeah.
yeah, thanks for that. And we have Lytton back with us.
yeah.
So what
So my
happens is
home
that
Wi-Fi
Lytton,
is showing some problems, so
ha,
I
ha,
don't know
ha.
why.
Now what you do is
Yeah,
you have got your presentation. So
yeah.
when you have the presentation there, may not be able to see the studio, but
Ah,
you'll
okay,
hear us. You'll be able to hear us. In case we don't get your audio or something, we'll let you know.
okay,
So
okay, okay,
yeah.
okay.
So
So
please go ahead. And about, yeah, we have little bit overshot time. So
okay.
within 10 to 15 minutes, if that is okay.
Yeah, yeah, yeah. Okay, okay, okay. Okay, so I will give you all a brief idea about the new emerging field of exoplanet. So, and what we think, how we can make a habitable exoplanet in our own galaxy. So, uh, to sh- to give you brief overview, if we really uh, want to think about exoplanet, then we really need to think our own existence. So first, I will start with our own galaxy, Milky Way. And as we know, the diameter of our Milky Way is around 150,000 light years, and one light years is almost around 9.46 10 to the power 12 kilometers. So the diameter is is really is very large. And number of stars, the current statistics based on various space-based and ground-based observations, number of stars in our own galaxy is around 400 billion. And so, and if we think 400 billion is around 440,000 crores in terms of numbers. And also the recent statistics that we have based on the observations that Kepler did, and also the TESS space telescope what TESS is doing. The current statistics is like the stars, all the stars that you see over the sky, at least each star has at least one planet around it. So if you go with this number, then we will have 400 billion planets in our own galaxy, right? And if we just think about our own galaxy, we can imagine like we'll have around roughly around 400 billion stars and 400 billion planets in our own galaxy. And the solar system is located around 27,000 light years from the galactic centers, which is well known. And we have the intense radio source Sagittae with a mass of 4.1 million solar masses at the center. So this is our own galaxy, our own home. And now, if we think about how many galaxies are there in our own universe, so by own universe I mean the universe that we can observe with telescope. So this is the northern one of the snapshot taken by Hubble and taken over the northern sky of California. So all these bright dots you can see in this slide, they're all galaxies, right? And the statistics is the total number of galaxies in our visible universe is around 200 billion. And then total number of stars in the visible universe will be around 80,000 billions because okay. So and then if we think about total number of planets in the visible universe, then it will be around 80,000 billions. So this is the number of planets we can expect in the domain of visible universe. So now, obviously, it is important to think the number that I have given to you. Like in our own galaxy, we can expect it to have around 400 billion planets. And if we consider the larger scale, like our own visible universe, then we can expect to have around 80,000 billion of planets in our visible universe. So obviously, then we should think: are we really alone in this visible universe? So the assumption that I will consider to think about this problem of are we alone is so if we really wanted to have a habitable planet, then we really need to think the planet must have a solid surface to start life, and planet has to be in habitable zone. So this is the, I would say, the restrictive version or restrictive definition of a habitable planet. Now, let's say we consider 1% is habitable out of 400 billion planets that I mentioned in our own galaxy. Then this number comes up as a 400 crores of habitable planets in our own galaxy. So now, if we pick very long odds for life formation, like 1 in a million, then we reach to around 4,000 life-bearing planets in our own galaxy. Okay. Now, if we multiply this number with 200 billions of galaxies in our own visible universe, then the number will be so large that we really need to if we really need to believe we are alone, then it's really intriguing. Now, obviously, then one can ask how many have intelligent life. For us, it's very difficult to know. Then one can ask, why don't they visit? So the amount, the scale that I mentioned, obviously tells you why it is very difficult to answer this type of questions that we often get from general audience. So, as I mentioned, so in our own galaxy, if we take the very odd probability, like 1 in a million may have life out of 400 crores of habitable planets that is expected from a general statistics, then we can have 4,000 life-bearing planets in our own galaxy. So, with the advent of latest technology and also the advancement of astronomy, with the advent of various space telescope like Kepler, TESS, as of now, we have detected more than 4,000 exoplanets in our own galaxy. And the different colors, and we observe different exoplanets with different size, different mass, and also different atmosphere. So different colors in this gallery corresponds to different atmosphere for this different type of exoplanets. So, and then obviously, if we really want to understand the big question, like, are we really alone in our own galaxy? And then in the bigger picture, like, are we really alone in the universe? Then we really think in a smaller scale by considering individual planet, right? So, so what we can do, we can try to understand the atmosphere of this exoplanet that were already detected through some of the space-based telescopes. So, and that's why the atmosphere of these exoplanets are really interesting. Because in most cases, we only have access to the mass and radius of these exoplanets, and in some cases we can measure the spectra from their atmosphere, based if these exoplanets are close to us. So by interpreting this spectra, we can understand what type of chemistry or atmospheric conditions those planet has, and also we can also understand their formation history, like the how that particular planet was formed around its host star, and also we can understand the habitability conditions. So if we really want to get one step ahead to understand the origin of life in those exoplanets, then we really need to think about how we can observe biosignatures in this exoplanet. So by biosignatures, I mean molecules like ozone and see methane, and also we also have biodetectors like water and CO2. So by studying these gases, we can try to understand the possibility of life, or possibility of some form of life in this exoplanets. And of course, whether the biosignatures, uh, 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 whether the detection of biosignatures also strongly depend on the atmosphere and also the interaction of the atmosphere with the surface. So that also has a role to play for the origin of life in this type of exoplanets. So in reality, as I mentioned, the number that I give it to you is, so two possibilities exist. So if we think about our visible universe, and then if we scale down to our own galaxy, then with a very least possibility, then we can have at least 4,000 exoplanets. We can expect to have some form of biosignatures or life related thing. So in the bigger context, we can think there are two possibilities. Either we are alone in the universe, or we are not. So both are equally terrifying for astronomers. So and that's why the field of exoplanet is so interesting. And we also have dedicated space missions, which will observe biosignatures in nearby exoplanets in the future. So I will stop here, and
Yeah.
would like to take any questions that you have.
Yeah. Actually, We are not having any questions from the participants as of now, though. I mean, there are many which I would like to
Yeah,
ask, and so actually, uh, when one is defining the habitable zone for these for any of these objects, we are not looking at some of the other aspects we know for stars. I mean, whether it is a supergiant star or not, or whether it is a variable star or not, or I mean, these kind of processes are also being put in some way
yeah,
as
yeah. So yeah, yeah, of course, yeah. So as I mentioned, the that's why I said the restrictive definition of habitability. So the main point for habitable condition, it depends on so many things. Like the most important thing is the temperature, and it depends on the host stars, and also the temperature structure. Like I haven't put that picture here, but it depends where you are forming your planet. So let's say you form a planet very far from the star, and then you have your basic volatiles like carbon monoxide, CO2, they will be frozen, because water need lot of temperature to get in the form of the vapor. And there is a particular location where you can have water in the liquid form. So beyond that region, a lot of molecules are in form of ice. So that dictates like whether you will have ice giants, or you have a rocky planet, or you will have a completely gas giant, like depending on the temperature structure. Now for different planet, for different stars, this temperature structure is different. Okay, so that aspect is one of the, I would say, the what you said is one of the most important point, because all these stars have different temperature structure. So that's the first thing. And then you also need to consider the orbit of the planet as well. So these are the all I would say uh, parameters that you really need to consider when you were discussing about the habitability.
Yeah, and actually, this is one topic which would interest many of the young people. I
Yeah,
mean, from senior school too. And
yeah,
it looks like maybe this may be exam time or so. We are not getting that many
yeah,
people coming in live. We are going to have a full talk from you
yeah,
sometime
yeah,
as part of the Astro Adda, because then we'd like to make it available to students at a time
yeah,
when they
yeah,
can
yeah.
come in. And so, I mean, there are many other questions to connect. Can I ask you to come in at this stage? And I was just thinking that with all these larger and larger telescopes and other projects which are
Mhm.
coming up, and so many definite, I mean, so many things can be said about, like what you said about biosignatures from these exoplanets. So, with this, it should be possible to say uh, quite definitive things about nearby planets like Mars and so on. The biosignatures and or is
Okay.
it that there are various levels at which we want to know this more clearly?
Yeah, so I would say for solar system is completely different story, because we can send rover in most cases. Like if we already know for some of these planets where they are located, and also the temperature is well constrained. We know their atmosphere already, like let's say Mars or Venus. So we can land on the surface of those of the solar system planets, right? And then our problem is much easier. But for this type of exoplanet that I mentioned, they are far away, several hundred light years away. So in that case, we really need to rely on spectroscopic signature of different molecules. And why biosignatures are important? Let's say we know, let's say if we observe CO2 from the atmosphere, and if we observe CO2 very, the broad spectrum of CO2 from any of these exoplanets, that we know the atmosphere is optically thick, and as a result, the surface temperature will be very high. So as a result of this, we will not have water on the surface, and that's exactly the case for Venus, right? So if we just observe the spectroscopic signature of CO2, which is one of the biodetectors, so and if we observe the signature of CO2 broad signature, then we'll know the atmosphere is optically thick, and as a result, surface temperature will be higher, and water cannot be in the form of liquid. And then let's say we think about CH4, methane, which is often considered as a biosignature, because we know CH4 is generated from various biological processes. If we see a lot of ozone in the atmosphere, then we think there is an ongoing photosynthesis
Yes.
process in that particular planet, right?
Okay.
So we really need to rely on, and if we observe water vapor in the atmosphere, then we can assume, or we can think that possibly the water oceans in that particular planets. But of course, it also depends on various other processes that I'm not the expert, like geological processes on the surface. So we really need to rely on the spectroscopic signatures, and mostly the spectroscopic signature from these very basic molecules. But for solar system planets, the problem is much easier because we can reach and send rover, and we can dig on the surface and measure the surface composition, and that can give us, real hands-on solution. But we cannot do such
Yes, of
experiment
course.
for exoplanets. So that's the challenge. Yeah.
Thanks so much. And while Arvind is asking a question, he is wanting to ask something. Kanak, can I ask you to come in at this point? Arvind, please go ahead.
Can you hear me?
Kanak, yeah.
Yes, can you hear me?
Yes. Able to
I
hear
had
you.
a question to Litan.
Hi, Kanak.
Hi, this is Kanak here.
Yeah.
So I listened to your talk in the morning. It was very nice, and I had an
Thank you.
impression
Yeah.
that I mean, I was wondering whether you do like more like a modeling the observed data, or you do theoretical. What is the kind of thing that you?
I'm doing.
Oh, I mean, are you doing modeling the data, or
Okay.
the theoretical kind of work?
Okay.
Like
Okay. Okay. So I would. So the answer is I do both observations and modeling. So for particularly for exoplanet, as of now, I am mostly doing the modeling for exoplanet atmosphere, because my research basically it revolves around studying journey of materials from early stages of planet formation to exoplanets. So for when I do study the planet formation and journey of molecules in planet formation, then I mostly use observation from various telescope, and also at the same time I do modeling. But for exoplanet atmosphere, as of now, I'm mostly doing the modeling, which is basically, by modeling I mean to study physics of the atmosphere together with radiative transfer to see what is happening in the atmosphere of such exoplanets. But just recently with my student, what we have started, I mentioned in my talk today, we have started looking into the data from Hubble Space Telescope. So we have the access to some of the data from our collaborators, and also from the archival data from HST. So for exoplanets, as of now, I should say it's mostly modeling. But from the early stage of planet formation is highly driven by observations.
Right. So the important part is that in India, there, because for this kind of work, you probably need Hubble-like telescope, right?
Yeah.
So
Yeah.
from Indian soil, we don't have this. So do you think what you should do, what we should do?
Yeah. So I should add here because okay. So I have access to the jet propulsion, like NASA JPL guaranteed time from James Webb Space Telescope.
I see.
So because I'm involved in the team of JWST MIDI instrument, MIDI infrared receiver. For my postdoc days there. So I have access to the JPL guaranteed time observation program for James Webb Space Telescope. So that's one of the thing. And also, I since I am closely involved, and also I know the tools because I worked with the tools during my postdoc days there. So we can always write proposal because the time is open to community. For any NASA facility is open to all. So there is no restriction for on the the country from where you are applying. So that aspect is solved. And now I am also under discussion with one of the missions called Ariel, which will study the exoplanet atmosphere for a lot of nearby exoplanets. So this is the mission led by European Space Agency. So they already invited me in their science team. So though India is not the full member, but through
Okay.
collaborations and the contributions of my group and the models that we built here, will have access to the time. So I can always, even if there
Okay.
is a risk, because we don't know what will happen when aerial time will be open to other countries, or whether it will be only restricted to European. So if it is only open to European, I can always ask my colleagues to get the
Right,
help and get the data. So that aspect is solved. And also I'm aware, because since I am really new to the Indian community,
Yes.
so I'm also aware, like, there is an ongoing effort at ISRO to move ahead with the exoplanets in the future.
Yes, I know. I mean, with this was, and this is really not in the public domain yet. So,
Yeah,
so,
yeah, yeah, yeah.
so
But
we were a part of it. So,
yeah. So I'm since because that's kind of, so that's kind of very good, because in that way I hope today with my talks people at least know I'm here. So we
yes, I
can
think this is
certainly
very
help
nice
to the
actually.
exoplanet community, because that's the thing that we really need to build. Because if you with respect to all other astronomical fields, the exoplanet is really tiny in India. Only handful people are working, right?
Indeed, indeed,
and
indeed.
and and only very few I know.
Yeah.
So one of the thing, my motivation is to really build this from scratch, and that's why I took up the opportunity here at NISA to build an independent group and train young students and postdocs, and so that we can start this journey from here.
That was very nice.
you.
Yes,
Thank
thanks.
you.
Thank you, thank you. Yeah.
Kanak, you were asking about students who are they're there on YouTube, and so if they have questions, they can actually put. Yeah, there is. Yes, there is a question which has come in from the YouTube. There are dust clouds. Actually, my eyesight is not very good. Arvind, can you help, or are you able to read it? It's there on the screen. Let me just full screen it and see. Yeah, there are dust clouds comprising organic, inorganic molecules and atoms
Atoms.
between in the vast space between our telescopes and these exoplanets. Then how can we be so sure about the spectroscopy data? Huh. Oh,
So
sorry.
okay, I missed this
Yeah,
point. There are
no, I think he's wanting to know that when we are, I mean, having these observations from far away, any kind of on the line, I mean, in the along the path, whether if there are some unknown disturbances, also how are we sure
yeah.
that this is
Okay.
increasing
Yeah.
to
So
the,
okay. So yeah. Okay. Okay. So as an astronomer, we really know what are the perturbation we expect from our own Earth atmosphere, right? And that's why we really, because all this observation that I was mentioning is mostly from space, right? So space-based observations. So we are above the Earth atmosphere. So in that way, we are really taking care of the various noise that he or she is mentioning. So since all these observations are from space, so we are really mitigating the effect of the Earth atmosphere. So that's one thing. And how do I know whether that signature is from that particular molecule? Because if we think about spectroscopy is kind of a real fingerprints, right? For each molecule excites at particular wavelength. So and when we observe band like mid infrared or near infrared, this is the wavelength where only handful molecules emit radiation. So in that sense, there is also very less possibility of line confusion. So that problem is also solved, but if we observe like early stage of planet formation, then we can observe molecules, different molecular lines, then there can be a lot of line confusion. But for this particular field, since we are observing from the space, and in most cases the frequency goes from near infrared to mid infrared to till far infrared, so there are less line confusion. So in that sense, we are really taking care of this problem with state of the art techniques.
Thank you. Kanik, would you like to tell the participants very quickly about this looking back
Mhm.
into the origins, or a little after the origins, and how, what exactly, and also a little bit about Astrosat and what exactly was found to for you to say that this is a signature of reionization from that particular object and so on. Would you like to tell us quick? You did mention that you are also in another meeting, so if you would
Uh,
like to tell the participant very quickly, please go ahead.
okay. I mean, I do not know how to turn on videos. And
Ah, okay.
is it the camera thingy?
Yeah, I'm not able to, we are not able to get video from your side. If you would like to share any visual, there is a share button. And also, I mean, mm,
Oops.
I'm also not able to figure out about the,
Okay.
there, that has
There
come.
I am.
Yes, yes, yes.
Yes. Yes. Yes. Thanks. Yeah, I'll be like quick. So is there any you can share as well?
Yeah, there is a share button at the bottom center.
Okay.
If
Um,
you can share your screen using that.
sure.
And
I'm
I
just
would also like to mention to all our other studio guests who are there that if you have any questions at any point, keep your video on, and we'll call you in to ask questions. And there are also participants on YouTube who may be asking questions. I think there may
Do
be
you
some
see my
questions.
screen?
Let me just see. I don't. Yeah, it has come in.
Okay.
Yeah, so now it's visible, and if you go full screen, you will not see the studio itself,
I
but
see.
you'll hear. We will let you know if we are not getting your audio or so.
So should I do full screen
Yeah.
like
You do
this?
full screen, and
Ah,
you can go
okay.
ahead. Uh,
Yeah. So yeah, thanks for bringing me here, and then thanks for the invite. And I think in a very brief way, what I'm going to tell about this new findings that we did. So so this is concerning the epoch of reionization of the universe. So here is a brief timeline of our universe. Our universe started with, as you know, from a big bang, and at that time, it was basically the soup of hot plasma, the most electron protons, then and when this universe started sort of cool down in a very in a quick fashion, then sort of electrons and then the ions started recombining. So by the time when the universe was just about 400,000 years old, the recombination was complete, and that's the kind of signal that we know from the CMB. So this is very unique and then very well understood physics in up to the recombination. And then once the recombination is complete, there were no light. So the universe went through in a dark phase because there are no stars, there's no galaxies, so we didn't have any light. So all the light that we see from the recombination is in the CMB. So universe went through a sort of a dark age over about few hundred uh, uh, thousand years. And then as the universe sort of, as you know, just cooling, and then it's also started expanding and it's cool. Then it went through the gravitational instability, started becoming important. And the standard cosmological the structure formation paradigm is that the um, the dark matter halos that were the dark matter that were there at that time, they started collapsing, and they formed sort of what is called the mini halos, right? And when the mini halos sort of grown to a sort of in a mm, in a, co- in a certain size, the hydrogen gas that were there, they started pouring in, and that's how the first stars and the galaxies formed. And when these galaxies, the first stars formed, they are probably be very, very massive, because there are hardly any metals. So it's like the kind of a pop three stars maybe, and the galaxies are made up of pop three stars. So they are very short lived, and as soon as they formed, within a very short time they bloom. And those were the sort of probably the sources of very extreme UV radiation, or I would say the radiation whose wavelength is shorter than 912 angstrom, or the energy greater than a 13.6 electron volt. And those radiations, when they come out of those these galaxies, they sort of started ionizing the hydrogen gas around in the surround. And that's how this the the hydrogen gas started reionizing again, and the light could come out, and that's how we could see. And this is the phase in which the universe went through a reionization phase, right? It was ionized in the very beginning, this reionized phase, and today the most of the matter between the galaxies are actually in this phase. This is called the ionized phase. Now, the question that is important, and that's where we come into picture, is that what were those sources? Because we don't know anything about those sources. I talked about those. These are basically like a theoretical ways talking, but we don't have any evidence. Nobody has seen first stars. Nobody has seen first galaxies. But that's the wish list. Now and we also want to know. There's one important factor here, that, as I said, these first stars and the galaxies would emit this uh, this extreme UV radiation. What we want to know is that how much of these photons, is actually escape the galaxy. So there would be always the production of these photons, and then the fraction of that we will escape. So that fraction is basically goes almost like a free parameter now into various cosmological simulations that produce the structures in the universe. Okay, so so there is a very urgent need to constrain this fraction of photons that were escape the galaxy. Okay, and in this and as I sort of said that in if I go to the next slide, I don't think I do not know how to go, but that is where we sort of wanted to. Now the point is that those photons, as soon as they emit, are there, if they somehow get out of the galaxy, they can easily get absorbed by the intergalactic medium, and that is the one reason why we have not been able to see any of these objects so far. Okay, so that is a very challenging task, and as a challenging is very intrinsic. There's very little we can do. So the idea was people started looking at
2 minutes. Two
objects
minutes
in.
should be okay.
Yes.
2 minutes
Yeah.
should be okay. Yeah.
Yes, I'll finish. So that is where people started looking into the lower redshift universe, and in the lower redshift universe, like redshift 0.4, we found there are some evidence now, dozens of galaxies, and also at redshift 3. But then there is a redshift which is around 0.4 to 3, which is huge range. This is where there was no detection, and that's where Astrochat came into picture. And we created the deep field, and in using the deep field, we actually sort of found an object which is emitting this extreme UV radiation. And there are several important factors to this. Is that, first of all, this is the first time we detected a radiation from a galaxy at 600 angstrom restraint. This was never a prediction before. People always thought that such radiation would not come out of the galaxy, but this is the first time we got, and that kind of helped understanding the massive star formation, for example, because we can put an observed data point on the model at the very short wavelength side, below 912. And then with the deep field that we have created now, we are like sort of exploring and higher redshift, and then like sort of this probably there will be many more sources that we will be in the coming years will be out from our work. So I think that's that's the kind of thing that we've been doing, and it's ongoing.
Yes.
Yeah,
So the very
thanks.
first of its kind detections, and yeah, it's very likely that it will be followed by many very soon. And
Yeah.
I specific to your talk, I don't see questions from the students. There are questions about possibilities of citizen science project and students wanting to take up something quantitative.
Mhm.
So most of the questions. So perhaps we will be taking these up as we have more participants coming in.
Right.
And thank you so much for taking time out when you already have
Yes.
another meeting where you had to be there. And
Sure.
also, sometime we are going to have we are going to ask you to give a full talk about this.
Sure. Thanks. Yeah. So
Soon I will
let me
be in
know.
touch
Yeah.
for that. And yeah, I mean, students are always wanting to know if there is a little quantitative exploration they can take up. So
Yes.
in
I think that would be great. Yes.
so thanks so much, and
Yeah.
please feel, I mean, if you could stay on for some of the other discussions too.
Yeah.
You
I
said
just
that
like
there is a
see like
meeting ongoing. So when you would wish to, there is a leave studio button at the bottom right. I don't know if you are able to see that.
okay. Okay. Yes. Yes.
Whenever
Sure.
you would wish to, and I'm
Okay.
going to call in. I think Pratik, Mayank, and Agyadeep, you were going to discuss back and forth between you aspects of the sun and the very exciting Aditya mission, right? Have I added both of you? Agyadeep, yes, and Pratik, yes. You put your video on. Pratik, I have your presentation which I can do screen share, and what is? Sorry, I'm getting a little confused about. Uh, yeah, Agyadeep, yeah, that's right, that's right. Put your video on. I was getting a little confused about what's. Uh, so, Pratik, you want me to share yours screen
Yeah,
share?
I think
Uh,
Argadeep can first present his interesting
yeah, yeah,
talk,
yeah. So,
then I will
Agyadeep,
just
what
come
you
to
do
after
is
that.
share your screen if you would like to do that, and I can add it into the window. Meanwhile, I'm just checking where is Pratik's presentation too, so that I can add it. Oh, it's a PowerPoint. Yeah. So, oh, have you added your screen share?
Shall I share the screen or is Pratik going to
Yes,
start?
Argydeep, your screen share. We are waiting for that. And meanwhile, I'm also trying to
Okay.
take out the other screen share, which is I don't yet see it in the studio.
I have them, then I can
Yeah,
share
yeah,
it.
yeah,
No
yeah, yeah, yeah,
problem.
yeah. It's come. And so you can go to the presentation. Yes.
Yes.
When you are at the
So
presentation,
I
you
should
may not be
start.
able to see the studio, but you will hear us. Please go ahead.
Okay. Thank you so much.
Volume is
So
a little low.
just a minute.
Is it
Is it
okay
fine
with
now?
others? It's all right. Yeah, you can go ahead. Go ahead.
Okay, I'll try to be a little louder then.
Yeah, it's good now. It's good now.
Okay. So hello everyone. I am Orkodeep and I am a PhD student in the Department of Astronomy, Astrophysics and Space Engineering at IIT Indore. And I'm working under the supervision of Dr. Bhargav Vaidya. And the topic for this short discussion is solar wind and its interaction with planetary magnetospheres. So I'm mainly working on computationally modeling the conditions in our heliosphere, which broadly falls under the branch of space weather. So I'll briefly touch upon what space weather is. The term space weather generally refers to the changing conditions on the sun in a given in the solar wind and within the Earth's magnetosphere. And this time varying and highly dynamic system directly affects life on Earth due to this Sun Earth connection. There is a continuous flow of solar wind plasma from the sun to Earth, which composes the background solar wind. That's what we call the solar wind. And there are certain disturbances and ejected material from the sun, such as solar flares and CMEs. CMEs stand for coronal mass ejections, which is basically the sun ejecting out a huge amount of mass into the ambient solar wind. And these have major implications when they propagate through this background wind and interacts with the Earth's magnetosphere. Flux transfer events, or FTs, then they facilitate the inflow of this solar wind plasma and the energetic particles associated with it into the Earth's magnetic system by a process called magnetic reconnection. So the magnetosphere is a region of space surrounding the Earth which shields the Earth and its delicate atmosphere from the direct impact of the solar wind plasma. When the fast-moving solar wind hits the magnetosphere, it forms a shocked region known as the bow shock, which you can see in this image over here. And the bow shock is the outermost layer of the magnetospheric system. Behind this bow shock is a very turbulent layer known as the magnetosheath, and then comes the magnetopause. The magnetopause is where the pressure from the planetary magnetic field is balanced with the pressure from the solar wind. And this blocks and it deflects the solar wind around the Earth rather than through it. So magnetic reconnection is a ubiquitous phenomenon. Basically, it is just, in simply stating, is just a rearrangement of the magnetic field lines. And as I have mentioned before, magnetic reconnection facilitates the inflow of the solar wind plasma into the Earth's magnetospheric system. And reconnection is a very common at the polar cusps and the magnetopause, and it also takes place at the magnetotail. A flux transfer event, or an FT, occurs when, due to the rearrangement of the magnetic field lines. I'll just go on to my last slide. As you can see here, there are some open field lines. These field lines open up due to magnetic reconnection, and then it is like a portal. A portal opens up, and the solar wind, which is just a bunch of high energy electrons and ions, they can flow into the Earth's magnetic system along these open field lines. These have huge implications on our life here at Earth, because these energetic protons and electrons can penetrate satellite electronics and damage them. And satellites inside the magnetosphere are generally naturally shielded from these type of high energy particles. And I have mentioned before CMEs, or coronal mass ejections. So coronal mass ejections, when they hit the magnetosphere, they can cause geomagnetic storms. Geomagnetic storms are basically magnetic disturbances, and these geomagnetic storms at Earth can induce extra currents in the ground that can degrade power grid operations. And they can also modify or even outright disturb the signals from the navigation systems such as GPS and GNSS, which are very crucial for mankind at this stage. We are very dependent on these type of technologies. And therefore, in this technological era, it is imperative and it's extremely important to have a proper understanding of the Sun-Earth connections, and also to be able to predict these storms and other particle events in advance so that precautionary steps can be taken. So Aditya L1 mission is India's first mission to study the sun in this context. It is a satellite with a bunch of instruments to be placed at the L1 point between the Earth and the sun, and it will be of great importance from a space weather perspective. So that basically concludes my presentation, and I think Pratik is here, so he will talk a little more about the Aditya L1 mission. Thank you.
Yeah,
Yeah.
thank you so
Thanks.
much.
Thanks, Arkadeep. Yeah.
I'm just trying to add. Why am I not able to find your presentation here? There is some issue. Okay, I think what I will have to do is I will have to share my whole screen, and which means that I will not be able to see anything in the studio. But I will share my whole screen, and then I will be able to share your presentation. So it will look a little odd to begin with. Uh, yes. Uh, oh, I'm sorry about that. Yeah. Pratik, is your presentation there? Are you able to see it? I'm not able to see anything of the studio
Yes,
now.
ma'am. Yes, ma'am. It's perfectly there.
Yeah.
Yeah.
So
Yeah.
you let me
So,
know when you want me
yeah.
to move the slide.
Yeah, okay, ma'am. Thanks, Arkadeep. So, as Arkadeep explained, how significant is the space weather for us? So, the India is planning its first fully space-based solar mission, that is the Aditya L1. So, this is a pictorial representation of the Aditya L1. So, where it's going to be in the space. So, 1 AU is basically the distance between the sun and the Earth, and we can see that the 99% is the distance between the sun and the Aditya L1, and only 1% between the Earth and the Aditya L1. So basically, the Aditya L1 is going to be around 23 and 23.5 Earth radius, which is basically outside the magnetosphere of the Earth, because the magnetosphere of Earth is basically on average it's around 30 Earth radius, and one can truly ask that we know what's Aditya, but why there is a name L1 in the Aditya L1. So in the next slide, that actually there are five Lagrangian points. If in the next slide we can see if ma'am
Oh, oh,
it's
I'm
in the
sorry.
next
I'm
slide. Yeah,
sorry. I'm
yeah,
sorry. Yes,
yeah.
yes,
It's
yes.
so there are basically five Lagrangian points in a two body system where if the total effective force becomes zero. So that basically means if we put something at one of these 5 points, it will stay there and just rotate with the Earth and the Sun system. So Aditya L1 is going to be at this 1 point, which is the Lagrangian one, which is between the line of sight of the Sun and the Earth. And to be truly honest, it's not going to be exactly at the L1 point. It's going to revolve around that, as we can see in this pink path of the SOHO. It's just because if just stays at the line of sight of the sun, then there will be a signal interference. So to avoid that and to have a better strength of the signals, it's just going to rotate around the L1 point, and it will complete the rotation in about 6 months. So, so now we know that why is the name Aditya L1 and where it's going to be in the solar system. So now let's see what are the different payloads and why this Aditya L1 is so unique in its own because of its unique payloads. So in this picture, we can see the whole space weather cartoon picture where the sun is having the solar eruptions, which Argadeep just explained. It just erupts from the solar surface, especially the coronal mass ejection. And Aditya L1 is going to observe that 24/7. And then it in this blue region of the Earth, one can see the magnetosphere and how it gets affected by the solar eruptions. So Aditya L1 has basically seven payloads, which is in the next slide, and in which the three payloads, which is the SPECS, the Papa, and the magnetometer, are in situ instruments, which is going to only measure the anything that is at that location, which is at L1 point. And the rest of the four payloads are the remote sensing instruments. Means it's going to observe the sun and then uh, from the basis of the spectra, it will deduce the data of the sun. So, starting from the aspects, it is a one can see it's a multi-institutional mission. The Aditya L1, the PRL is involved in the aspects, and the aspects is going to measure the ions and the protons and the helium charged ions. And the Papa is a plasma analyzer. It's also going to uh, like get the data about how the plasma is varying at the L1 point due to the different solar activities. And this magnetometer is basically a magnetogram, and it's going to measure the magnetic field at just the L1 point. And apart from that, there are four remote sensing. The VLC is the coronagraph. So we know in the solar, when the solar eclipse happens, then we can see a round of the sun that is also very bright, and sometimes we see that rainbow type of structure also. So that's very beautiful. So coronagraph just has an occulting disk which occults the solar disk, and then tries to study the a bit dimmer atmosphere of the sun. And the suit is the ultraviolet imager. So it is going to observe the sun in the ultraviolet and forms its image to study the highly energetic events that happen in the solar surface and in the chromosphere also. And the Helios and the Solex are basically the X-ray spectrometers, and they are going to mainly focus on the highly energetic events that happens on the solar surface, like flares and the speckles, the streamers, etc. by studying the X-ray properties of the sun. So that's pretty much broadly about this unique mission of India, which is unique because of its unique payloads at this current situation. So, thank you.
And that was lovely the way you and Agyadip you walked us through Sun Earth connection and then placing Aditya in the middle, even though at 0.1% the distance. Lovely. And Mamta, you wanted Manami and Gunjan. Would it be okay if Mamta wanted to share with us some excitements about machine learning usages in astronomy? Would that be okay, Man? I'll actually add you in, and you could also. I'm getting a little confused about adding people into the studio. So would that be okay, Manami and Gunjan? I will ask Mamta to. Uh, you had to leave early, Mamta. So
Yeah,
do that, please. Then you,
yeah,
if you want to share your screen, you go
yeah.
ahead, and I will add. Neeraj is also there, and yeah, all right. So let's do it like yesterday in a group kind of a discussion. Mamta, you go ahead, and after that we will take in from others. So,
Yeah, is the screen visible?
yes, I'm just adding it. Yeah, add it. And so maybe, I mean, given that we have many others also, so maybe 10 minutes or so, if that would be okay.
Yeah. Okay, fine. I'll try to wind up in 10 minutes.
And
Okay.
so everyone else, please stay on and make it interactive. Go ahead, Mamta.
Yeah, shall I start? Am I audible?
Yes, yes, please go ahead. Go ahead.
Am I audible?
Yes, yes.
Okay, so I'll start. So this is an overview of a session in one of the talks in today's session in extragalactic astronomy about teaching machines to study galaxies. I'm not able to hear anybody. Can you please tell me if I'm audible?
Yes, yes. We are able to see and we are able to hear you.
Yeah, good. So I'll move ahead. And this was presented by Dr. Yogesh Vadadekar from NCRA, Pune. And so to begin with, I'll start discussing the what type of machine learning algorithms are available. So there are two kind of machine learning algorithms available. One is a supervised ML algorithm and the other one is an unsupervised machine learning algorithm. By supervised machine learning algorithm, we mean that we have a set of data for which we have the inputs and the outputs that are expected, and we take our algorithm or we take our machine learning techniques through the process of getting the outputs from the inputs and giving back the feedback to the algorithm so that it learns itself. So that's a supervised algorithm. An unsupervised algorithm, by that we mean that we have a set of inputs but we do not know what are outputs. So in that case, the machine learning algorithms learn through the groups and the patterns they recognize in the process of data analysis. So these are two kind of algorithms. In astronomy, we are right now in the process of using both the kinds of algorithm. I'll talk about the first one today. Dr. Yogesh talked about the first techniques in their papers which they discussed. So the first one, that the results are there in this paper, which states that they predicted the star formation properties in the galaxies using deep learning. Deep learning is a part of machine learning algorithms, which are essentially the first kind of ML algorithms. So in this paper, they uh, actually predicted, they took the gamma telescope data, gamma survey data, and from there they took around 75,000 sources, galaxies, and they mainly predicted three kind of parameters. The first one is the star formation rate, the second one is the and I'm not sure whether it is visible or not, but it's written over here: stellar mass, the star formation rates, and the dust luminosity in the galaxies. So these three parameters directly relate to the evolution of the galaxy and so on. And I have a few snippets from the paper which kind of highlights their results. All the three plots are the plots. The y-axis is the actual value of the data that they had from the survey, and the x-axis is the predicted one from the models, the machine learning algorithms. And the line that you see on the this is a scatter plot, so they just plot that corresponding to a particular output, expected output, what output the machine learning algorithms do give. So you see, if there is an exact match, you see that the line, it should be a perfect 45-degree line. However, they see a small scatter. This scatter can measure the errors bar of their machine learning algorithms. So they do kind of calculate the variance in their data that they get. And the best fit lines, of course, are pretty close to 45-degree lines that they have. And the next thing that they highlighted was the classification of radio galaxies using the machine learning algorithms. I'll highlight what are the advantages of using machine learning once I have state the results of their second paper. So there are four kind of eventually radio galaxies that they wanted to discuss, that they have discussed in their paper. FR1 and FR2 are two types of galaxies. So FR1 and FR2 differ. They have an AGN at the center, and they differ in the morphology of their jets, which are ejected out of the AGN. So in FR1, the jet is much more bright at the part when where it starts, and it kind of fades away as it goes away. In case of FR2 galaxies, the jet is much more prominent towards the tail of the jet. These are the bent galaxies. Bent galaxies, the jet is kind of in FR1 and FR2. You see the jets at approximately 180-degree angle, aligned at 180-degree angle. In bent radio galaxies, the jet is not exactly 180. It's a little bent. And the fourth
Mom,
type of galaxy which they
yeah.
wanted to discuss was the compact galaxies. So this is the snippet of their paper. So they had a sample of around 2000 galaxies which they wanted to classify using the machine learning algorithms, and they could predict the this is also a first kind of machine learning algorithm that they used, and they could predict the morphology of the galaxies using the machine learning algorithms with an accuracy of approximately 92%, which is fairly good.
Uh-huh. Mamta,
Yeah.
actually, I had overlooked. Neeraj had just sent a message saying that he also has a meeting at 9:30. So
Okay.
could we kind of give him a little time to
I'll just
speak
finish
and
in
then come back? Yeah, 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 yeah.
I'll just finish in 1 minute highlighting the importance of machine learning algorithms. I'm done. This is the last slide.
Hmm, hmm, hmm.
Just one more. Yeah. So then we can discuss later on.
Yes,
So
yes.
the advantages of using machine learning algorithm in both the papers are the following: that the data analytics, the first thing is that with the upcoming projects that are there in astronomy, like SK, MWA, Meerkat, and so on, you have a very big data sets available to us, and many more sources will be detected. So an efficient algorithm to detect the morphology, to detect the source, which kind of source are these, is very important. So this second result has a sample size of 200 and accuracy of 92%, is very good, because the earlier works that are done in the same field have a sample size of more than 25,000, and still the accuracy is around 94 to 95%. So that kind of highlights the importance of the second work. In the first work, what is important is the timing. If you do a normal analysis of calculating the star formation rate and other parameters, it takes around 10 minutes of the run on the computer time to actually calculate these parameters. However,
their algorithm could predict the same amount of parameters in just 30 minutes time, and most of it was given in the deep learning part rather than the prediction part, rather than calculating the actual values. So that's the highlight of the methods that they have used. So I'll stop over here, and maybe we can take over discussions a little later.
Yeah, yeah.
And
Thanks, Mamta, so much for bringing that into notice for the participant. Neeraj, apologies, but now maybe 10 minutes.
Yes, of
It's a
course.
very, very,
I
very
know,
tall
I
order
understand.
to say that. Tell us something about the kind of complexities
No, actually,
in
I would
10
have
minutes.
liked to hear
But
more about machine learning if there was more time.
but we'll have sessions
Yeah,
again.
yes,
You just tell us about the coal gas explore. I
yes.
mean, kind of how those signatures. I know it's a very tall order, but at least
No,
tell the
no.
participants a little
Can I
about
can I
what.
share my screen? Is it possible to
Please
share
do,
my
please do,
screen?
please do, please do, please do.
Yes.
So, yeah, Mamta, it's okay with you to stay on for a while in case there are other questions, etc. For
Okay,
yeah,
I have
yeah,
gone ahead and
absolutely.
shared my
yes,
entire
yes, yes,
screen, I
yes,
think.
yes, yes, yes,
Please.
yes, yes.
So
Excellent.
I'll go through this very quickly and I'll keep it at very general level.
Please,
So
yes.
uh, my main motivation comes from our involvement in something called Meerkat Absorption Line Survey. It's a large project which we are doing with Meerkat Array in South Africa, and and this telescope is actually a precursor to what we call a square kilometer array, which Mamta was also mentioning, that will produce large amounts of data. So this is what we call as precursor or pathfinder to square kilometer array, because we are going to do everything that we want to do with SK at a slightly lower level with these telescopes, because SK is going to be so much more complex that if we just build SK, we wouldn't know what to do with it, because it will produce so much data. We cannot use that data. We will not know anything about it. So we are all working towards SK using these precursor telescopes. My main interest is in cold gas in galaxies. So what do we mean by cold gas in galaxies? So on left panel, if you see, and let's just focus on the x-axis. X-axis is redshift, right? It's the age of the universe we are talking about. And here 0, it means that like we are sitting here somewhere. And on what this curve is showing here is how the star formation rate of the universe as a whole is changing as a function of redshift. And you can see that like it was not maximum today, it actually peaks somewhere in the past, right? And then again it falls. So this means that like the star formation was at a very low level in the very early universe, then it started increasing redshift, and then again here it has come down to a certain level. And this axis is actually in log, if you see, right? So it's changing by more than an order of magnitude here. You can see that. So there's a huge variation here in the star formation, and this is very accurately measured. So the question, of course, like it is not enough for us to just look at something and say, hey, this is happening. We also want to understand why it is happening. And in this context, it becomes really important to understand what cold gas in universe is doing. Why cold gas is important? Because we all know that hydrogen is the most abundant element in the universe. So of course, anything that we want to build, it has to somewhere start from hydrogen gas. So that's a given. But hydrogen can be at a very diffuse level in the universe also, right? But if you want to bring it together to really high densities where it can actually eventually start fusion. So if you want to have a gas cloud which can collapse to such high densities, we need to have it cold. We need to cool it. We need to cool it. I mean to say it has to cool from the temperatures of, let's say, 10 to the power 6 or 10 to the power 4 Kelvin to, let's say, just about 10 Kelvin. And why is that important? Because if gas is warm, this means that it will also have a lot of pressure, right? If you remember, P is equals to NKT, right? So it depends on density as well as the temperature. So now if you want to collapse the cloud, we really, it must cool also, because otherwise it cannot collapse, because it is collapsing under the effect of its own gravity. That's the reason. So if a cloud is collapsing under its own gravity, if we can also continue to cool it, then it can continue to collapse, and then eventually it can lead to formation of stars. So the problem to understand what is there in the left panel can be simply broken down to the fact that if you can tell me somehow that what is the available amount of cold gas at different stages of the universe, then I can tell, and where it is located, then I can tell you why this is proceeding like this, right? So now there are lots of projects which are going around in world using various telescopes, using various techniques, trying to measure how the cold gas is evolving as a function of redshift here, as the age of the universe, and where it is located. Because the problem is very simple, that we have hydrogen distributed in different forms. We want to bring it into galaxy, we want to cool it so that it can form stars. But there's a lot of physics involved in that, right? So one of the techniques that is very effective for this kind of measurement can be done using absorption line. So very quickly, what we mean by absorption line here is that we know that electromagnetic waves interact with matter. So if there is a distant object like a quasar and light from that is passing through, then it will come across like some very low density gas, which we can call as, let's say, intergalactic medium in the universe. Then it will produce some absorption lines, which you can see here in the spectrum, right? But as it passes through, by chance, it can also come across a very high density clump here, which could be a galaxy or a group of galaxies. Then we can see a very strong absorption here, right? It's telling me that there are lots of atoms along the sight line, and this is a signature that there is possibly a galaxy here at this redshift here, right? And of course, you can also see in the spectrum that there are these emission lines which are actually associated with the quasar here. But let's say we are not interested in, at this point in these. We are interested in all these absorption lines which are produced in the spectrum, right? All these. So these are the absorption lines of Lyman alpha here, which is telling me how much neutral hydrogen is there. And then there are these lot of metals which are produced there, and they play a very important role in the cooling of gas, right? So by measuring hydrogen gas, how much metals are there, and then different level populations or different absorption line that I see, I can tell you, I can measure that how much cold gas is there in the galaxy at that redshift. And why this technique is so much more powerful or complementary to when we look at objects in, let's say, emission line. By emission line, I mean that just the way we look at sun, for example, in the morning, or a light bulb in our house. The fact that if I keep moving it away, it's the signal, the strength of the signal will fall off as 1 by r square. But in case of absorption, that does not happen. It only depends on how strong the background source is and how much gas is present along the sight line. Then regardless of whether it's present very close to me here or it's very far away, I can still continue to detect it, right? So this is a very, very powerful technique. So what we are doing with Meerkat is to actually look at lots of such sources in the sky, and it's a radio telescope. So we are looking at bright radio sources in the sky, the kind of sources which Mamta was talking about, the kind of AGNs with diffuse lobes or compact cores, or all kinds of morphologies. And our idea is that we are looking for galaxies which are in front of them by chance, and then we will be looking at specific absorption lines of hydrogen and hydroxyl to measure how much cold gas is there in the galaxies. And then as a function of redshift, we can measure that. Before I go into a little bit more specific couple of things, and I will not take more than 2 or 3 minutes on that, I just want to quickly touch upon that. What is the technique that we are using here? And the technique is called radio interferometry. So this is a radio telescope. This is actually one telescope, although you can see that it has got 64 dishes here, and they are all looking at the same part of the sky. And this technique that we use here is called radio interferometry. In this, what we do is that each telescope is looking at the same part of the sky, and then we take signal from each telescope and we combine them in pair, right? And combining them in pair is equivalent to, if you recall, a simple Michelson interferometer, or even a simpler thing like a Young's double slit experiment that we do in our laboratory, right? It gives us a fringe pattern. So what we measure as an output of these two dishes is a fringe pattern. What we do in this case is that we take all those fringe patterns from these different telescopes and we do a Fourier transform of it. And that Fourier transform is then corresponds to the image in the sky. And that image is actually as real as what you would get from an optical telescope, because what happens in case of an optical telescope or even the lens that we have in our eye, because of the optics or the way nature has made the interaction between glass and the electromagnetic waves, it mathematically what it is doing there, it is carrying out the operation of Fourier transform, right? The nature is doing it itself there in the glass lens. But here what we are doing is that we are doing it in two parts. We are actually collecting the signal, collecting the fringes, by combining them in pair, and then doing the Fourier transform. So we are electronically simulating a lens. So you can see that all these dishes which are spread over such a large area, right, 5 kilometer or 8 kilometers, this is actually equivalent to making a lens or a dish which is the size of 8 kilometer, right? This is so huge actually, right? And you can imagine that it's such a mathematically and electronically such a fantastic thing, because in just by using simple engineering, it's not possible to make a telescope or a dish which is as large as 8 kilometers. So this is such a fantastic idea, and it's so fantastic that actually a Nobel Prize was given to this to Professor Martin Ryle for actually showing that it actually works, and it can be made to work for making astronomical images. So this is the technique that we are using, and using this, the idea is that we will look at this large number of radio sources in the sky, look at different absorption lines, and then we will be able to measure how the cold gas in galaxies is evolving. This is one of the really cool problems that astronomers are trying to understand as of now. And this is just one example I wanted to show here, which is this radio source. This radio source is actually quite funny. You can see its shape. But why it looks like this? Because there is actually, as I was saying, that there is a radio source and there is a galaxy in front of it. But if there was a simple galaxy, it wouldn't look like this. It would just look like a simple blob. In this, it is looking like a ring here. This is because this galaxy which is in front is causing what is called as gravitational lensing. So what is happening, that the light which is coming here from the object here, let me use this figure. The galaxy is so massive here that the light from it is actually getting bent the way it would bend in a lens. And it is producing this multiple image around this galaxy. And that's what is causing this Einstein ring. So through this, we can actually look at the distribution of gas, not just at the single point in the galaxy, but at multiple points in the galaxy, and generates this different set of absorption lines which are seen at different frequencies. And I'm not going to the details of these absorption lines, but using this, we can infer a lot about the physical conditions that are there in the galaxy. And it's a very, very powerful tool which has now become available to us, because in past, when we wanted to do an experiment like this, either the telescopes would not be very sensitive, or they would be located in a place where there would be a lot of what is called radio frequency interference, because we have to worry about such things. But with now SK or SK precursors coming in, where telescopes are located in places like South African desert or a desert in Australia, it's so much away from all the civilization that we get these beautiful spectra where you see that it's fairly clean, right? You can see that if there's an absorption line, we can with confidence say that, okay, this is coming from an astrophysical source and it's not due to radio frequency interference. So it's something which is becoming possible now. Yeah.
Thanks, Neeraj, so much. Actually, we are going to have a full talk from you for this very exciting.
Yeah, I would love to actually, and we can do it much more interactive. It's so much fun when the
Actually,
questions keep coming in. And
yes.
yeah.
So right now, I want to move on to Manami and Gunjan, because they were supposed to come in earlier and apparently they have to leave very soon. So please go ahead, Manami and Gunjan. But Neeraj, I will be in touch with you for a full talk.
Absolutely, looking forward to it. I will stay on for a few more minutes before I leave. Yeah.
Yes, please do, so that we can kind of conclude after Manami and Gunjan. Go ahead, please. Do you want to share some visuals, Manami and Gunjan, or speak? You are able to hear me? Actually, you know what? You are muted, both of you.
Yeah. How can I share my screen?
So there is a share screen at the bottom. If you click on that, your screen will come.
Okay.
And
Okay.
so you wanted to report one of the about
Yeah.
yes.
Can you see the screen?
Cosmic rays in the circumgalactic medium. Yeah.
Yes.
Yeah. So can you
Please go ahead.
can you see the screen?
Wait. Why it's not showing up here? Yeah, I think is this the one? Yeah. Yes. I'm sorry. It did come in.
Yeah. So yeah, I would be briefing about my talk from the 20th session. It's my talk is about like how much cosmic rays are there in the Milky Way circumgalactic medium. So before going into the result, I would briefly tell about the circumgalactic medium. So the circumgalactic medium or CGM is the region between the galactic disk and the intergalactic medium. You can see that this diffuse gas. So how much diffuse this gas is? if you imagine a bottle of 100 liter, and if you put a one particle in that bottle, so it would be 1 or 10 particle, it would be very less dense. So that kind of density a CGM has. So it is very diffuse. So my mental picture of the CGM is kind of a cupboard of not so very organized person. So if we see the cupboard from outside, we kind of see a very peaceful, quiet, organized thing. But if we open the door of the cupboard, we can see the real mess. Similar is for the CGM. If we look overall at it, it seems to be a very quiet place because very diffuse nature, no such interaction between atoms and something like that. But if we zoom in and focus on the small details, we can see the lots of mess are going on there, like gas inflow, gas outflows, and also the recycling of gas from the disk. So it's a very messy processes are going on there, and these messy processes are very important to understand how galaxy is evolving. So that makes CGM or circumgalactic medium very important to study. So now I would say that this disk part, so there are cosmic rays everywhere, high energy particles, high energy protons, and these cosmic rays particles are lifted by the outflows, supernova feedback and everything like that. So it will lift it to
Magnetic
the
field
CGM.
too, maybe, right? Lifted through the magnetic field, perhaps? That could
Yes.
be one way to, yeah.
Right. So it will be lifted to the CGM, the circumgalactic medium, and so it can be there in the circumgalactic medium, or it can escape to the IGM, like the intergalactic medium. So our work shows that how much cosmic rays can be there, can stay there in the CGM. So we uh, kind of use some observational techniques to do that, like we develop some models and develop compare the model result with some observational constraints. So like we uh, we have an gamma ray and radio background observation. So what gamma ray will do, like if the cosmic ray proton will interact with a CGM proton. So let me show you a video if it's uh, there. Okay, 1 second. So uh, so uh, can you see the video?
We see the icon, but I don't think it's playing.
Okay, so this cosmic ray proton will interact with the CGM protons, and it will create pion, and that pion will decay into two gamma rays photons. So basically, we cannot see cosmic ray, but we can actually see this gamma rays, and we can tell that how much cosmic rays are there in the CGM. And also if this cosmic rays will interact with the galactic magnetic field, and will if some charged particle will interacting in the magnetic field, it will emit radio synchrotron emission. We all know it will. And so from that radio synchrotron emission, we can also tell how much cosmic rays are there in the CGM. So we use these two observational constraints for like telling that how much cosmic rays are there, and we use two simplistic theoretical models of the CGM. I won't go into the details. So it's kind of like we can't see cosmic rays, but suppose we can't see storm, but we can feel its presence uh, by moving leaves. So uh,
Because of the
just
interactions that they have with the medium there, right? Maybe even like when you mention magnetic field, I think even if the proton or the cosmic ray particles do not radiate, it will be deflected quite a lot. So you cannot
yes.
detect like where exactly does it come from. So
Yes,
you lose
right.
information on that.
Exactly.
And
Yeah.
yeah, and I
Yes.
think it's
Yes.
important to constrain the cosmic ray population in CGM because it will also give an idea about the cosmic ray spectrum in the galaxy. Like how much of the
Yes.
cosmic ray in galaxy that were produced has escaped already. So that will affect the
Right.
galactic cosmic spectrum too. Yeah,
Spectrum 2, yeah, and that's also still a very unknown topic, I guess. The galactic spectrum, like we're not sure about how it will look. Definitely, am I right,
exactly.
Gunjan?
Yeah, and yeah, I think so. Like even with the spectrum that we have for now, we are trying what all like we know supernova could accelerate them, but what else? Like what all these accelerators are at such interstellar in the interstellar that accelerates particles to such high energies. So that's there.
Can you repeat? Can you repeat that question, please? Your voice is a bit breaking. I think so, or
Can
it's
you
my
hear me
end.
now?
Uh,
Can you hear me now? Is it clear?
yeah, I could hear it. So there may be also network
Okay,
issue on your end,
I
Manami. That is
can't
also
actually hear.
possible. I think there is a network issue your side because I could hear Gunjan clearly. It was lovely the way you told us about cosmic rays, the intergalactic medium in this interactive kind of fashion. It was really lovely, and so we have kind of gone through so many aspects, uh, and we are kind of now come to the conclusion of our Astrochat sessions. And one thing which I saw yesterday, day before also, I think most of the students people who have been participating, we got less participation this time, probably because of exams. But there are some, I think, who are kind of, they do stay on because they are interested and they want, most of the time, uh, they want to do something quantitative. So I think it will be
Yeah, I,
nice. I'll ask all of you to give us separate talks, and along with that, think about something perhaps. I mean, there people have been saying that there not any citizen science opportunities and so on, even learning opportunities, but quantitative would be nice. Mamta, you were saying something. Sorry, I interrupted you.
I want to add something here that the this topic that I picked up, particularly the machine learning topic today, was that one of the reasons for picking up this topic is the same as you mentioned, that there are students who are interested to take small projects or do something.
Yes, yes,
So
yes.
machine learning, at least for the people who are interested in CSE and computer science, is a very good topic to pick up at this stage because it's a quite growing field and they can really explore that part if they are
Hmm.
interested.
Santosh Kumar Gowda wants to know what is supernova. So, which one of us is going to go supernova? So, any of you are taking it up? Supernova. He wants
Yeah,
to know what is the supernova. So, generally, massive star
very
when it has
glorified
finished.
death of star. Like I
All,
would say, like it's very
yeah, you
glorified
go
death.
ahead. Yeah, yeah.
Goes, explodes with such high
Ah,
energy, like it puts up so
ah,
much energy in the
Santosh Kumar,
space.
I have supernova waiting in the wings for you. Let me just find where it is. So, massive star when it is kind of got rid of all its uh,
Like you're saying that so it's kind of
that's supernova. Of course, that's a kind of a visualization. It's not
yeah.
really
So
that we are getting supernova data and put it there. But
if
so the
to
core is imploding and the external layers are being thrown out in an explosive manner. That is the supernova. And when a massive star is doing this, the remnant left, if it is very mostly more massive star, maybe neutron star, even a black hole may be left. Lower mass stars will just kind of whimperingly go out, throw out a planetary nebula, and become white dwarfs. So that's a supernova. And it was very nice that you came in and asked this question at this stage, so we could end with that supernova.
Yeah.
and yeah, end with a blast. Yeah.
So we will all, continue in this group, perhaps if you don't mind, and we'll have more of this Astro chat. But one thing I realize is that the Astro chats, what is happening is that we are jumping from topic to topic to topic, which was because so many things were discussed. But would what would be more useful for them, perhaps, is if we pick up one and have a session and perhaps a follow up with some quantitative observations. So at this stage, I think. we may end the broadcast, and we actually
Yeah.
kept you for so Manami and Gunjan, you are supposed to go in much earlier. We kept you for so late.
No, not.
But it was lovely. It's lovely. I mean, the way we had this
Yeah,
discussion. Thank you everyone for being there. Thank you for all the
Yeah,
viewers.
thank you so much.